训练一个慢，然后它速度就会慢，然后有
听起来超好。
图片，然后就会。
Okay, this is back to convolution. Okay, as I just mentioned, if the input have the depth of 3, so the filter must be also of depth 3. Okay, must exactly the same as the input. Let's take this example. If the input image is 32 by 32 with 3 channel, and if the filter is 5 by 5, as I mentioned, it got to be 3. It cannot be any other value. Okay? And after the convolution, the result will become 28 by 28. Why is that? If this, okay, if we have a 32 by 32, initially, we need to starting from here, okay? So in the center, so on the right, on the left and on the right, you will have 2 pixels missing, okay, in the border. Everyone follow me? 因为你放的时候，它左右两边，因为5乘5嘛，5乘5哈，你放的时候两边会不见。So you will mixing 2 pixels on the left, on the right, on the top, and on the bottom. So therefore, after you do the convolution, it will reduce to 28 by 28. So if we keep using this 5 by 5 filter, when you go for 100 layers, for example, which is not possible, then you will keep reducing. What will be the feature map size? Then after you do the 5 by 5 convolution, it will become 24 by 24, right? You will reduce by 4, and then 20 by 20, and then 16 by 16, and 12 by 12, 8 by 8, and eventually you will be gone. So you must be very careful, okay, about the number of layers or what you do. Okay, we will say something about that, how to handle that. Otherwise, all the images will getting smaller and smaller, okay, and eventually the size could be only 2 by 2, okay, could be only 2 by 2, or even just 1 by 1, okay. Now, let's take this example. The input again, 32 by 32 with a depth of 3. If we do the same convolution here, 5 by 5 by 3, the output will be 25, but the depth becomes 6. That's very important, must keep in mind. You can change the channel as you want. Why it becomes 6? That's because it uses 6 filters. Now, the 6 is determined by the user, unless you use AutoML. Otherwise, the user need to determine how many filters you want to use. Okay? You know what I'm saying? Okay? So, because you use 6, then eventually you will have 6. The depth will become, so, which means you can always keep to change the channels. Depends on how many features you want to extract it. Okay, for this case, we use this filter. It does not have to be 6, so that will be another parameter for the user need to determine. Okay. The more use, the more parameter you need to determine, and the more computation time required. Let's say. Okay. But if you use a very small number of filters, you may not fully describe all the possible features that the user need to determine. Okay. So here it's an example. Okay. Suppose the input is 7 by 7 by 3. For example, this R, G, and B. Okay. And we use two filter. We use two filter, just two filter. Okay. Filter W0, W1, but because the input has 3 channels, so the filter must also have 3 channels. Then we will do the convolution, okay, with the corresponding position or channel, and then we sum them up and plus the bias. Okay, we need to plus the bias. That's 9 plus 1 plus minus 2 plus 1. That's what you get here. But listen up, because the filter is 3 by 3 and the input is 7 by 7, what should be the expected output? What should be the size? As I mentioned, the original 32 by 32. If we use a 5 by 5, then it will become 28 by 28. So if it's 7 by 7, the filter size is 3 by 3, what should be the expected output size? Should be 7 minus 2. So we expect 5 by 5. But how come this example show you the result is 3 by 3, 1, 1? That's because what? That's because we put something here. We use a stripe by 2. A stripe by 2. Stripe is a word when you use a KRC. By default, the stripe is 1, means 1 pixel. It means what? You move the filter 1 pixel every time. But for this example here, you use the stripe by 2, which means if you go for 3 by 3, the first position right here, the next position will be right here. Okay, you will move 2 pixels, but not 1 pixel. So for this case, the size is reduced from 7 by 7 to 3 by 3. That's another way to reduce the information of the feature map. The other one, you can use the pooling. Okay, I will get into that. Usually we use pooling to try to reduce the information or try to reduce the image size. But you don't need to pooling. You can just go for convolution, but with the stripe by 2, in that case, you will reduce basically half. If stripe by 3, then we will reduce the size, okay, by a factor of 3, okay. But usually, we will just go for by default with the stripe by 1 or 2. Basically, we don't use anything beyond 3 or 4 or 5. Okay, you will lose a lot of information. Okay, so keep that in mind. The stripe 就是你要跨步的步伐，一次要移几个 pixel， 那个 filter. Okay, how you slide the filter. Okay, so remember this is a good example. You can calculate yourself if you not quite understand how the relationship between the image size or the feature map size and the convolution size, okay, and the stripe, okay. But for this case here, because why the result becomes a channel of 2? That's because the original channel is 3. The number of channel is 3. And why outcome? First, because we use a stripe of 2, so the size has been reduced from 7 by 7 to 3 by 3. But how come the final channel is only 2? That's because what? That's because we use only 2 filters. Because we only use 2 filters. 因为我们这里面只有2个滤波器，所以它最后结果呢，就会把3个变成2个。Okay? If you use only 1 filter, then the output is just 1. So it's all up to you. It's up to the user. Okay. The thing that you cannot change is the depth of the filter must be the same as the channel of the input. They must be exactly the same. Cannot be less, cannot be more. Okay. Okay, so if you are interested, you can Google it. You can see the animation. Okay, you can see the animation, how it works. Okay. Okay, so for this case here, again, the input is 32 by 32 with 3 channels. And first, we applied a convolution with 5 by 5 by 3, and we use 6. So the output will be 28 by 28 with the depth of 6. And then we go for the next convolution with the same filter size 5 by 5, but now the depth should become 6. It cannot be 3. Why 6? That's because the depth for this input is 6. So it got to be 6. Okay? 它一定要6啊，因为我们这边的 input 的深度是它有6个 channel. Now why it becomes 10? That's because we use 10 filter. So after that becomes. So if you for some image segmentation application, or for you transfer an image into another image, eventually you must, because the input is the image, if you expect that the output is also an image, then what should be the number of filters you use in the final convolution? It got to be 3. So it becomes, it may not be represent RGB, but it got to be 3. Just same here. So the final depth, okay, or the number of channel must be 3 before you output a new image. Okay? 好，这是看你的应用， okay? 看你的应用，这样。But if the output you convert, for example, you convert a color image into a grayscale image, then what should be the number of filter you use? It got to be 1, just 1, because you need only a grayscale image. So everyone follow me. Okay, that's the idea. Oh, that's the idea. Okay. Okay. Pooling. Okay, the pooling. Usually after the convolution, we will go for the pooling layer. Okay. Pooling layer, usually we using the size is 2 by 2, okay, with the stripe of 2 by default, okay. So it means what? We use a 2 by 2, okay, 2 by 2, and it moves 2 pixels at a time, which means after the pooling, the size will reduce by a factor of 2. Just like the convolution with a stripe of 2. So in that case, you don't need to do the pooling. So the purpose of pooling is try to reduce the information, okay, or try to reduce the complexity of the feature map. Okay, so if you have nothing else, you don't need to pay too much attention on it. If you want to go for the pooling, just use the default. Okay, I will highly recommend it. For pooling, even the size is 2 by 2, it involves no parameters. It does not need any decision parameter, not like the filter, but just some operation. Okay? The typical choice you can have for the pooling is maximum pooling or average pooling. The maximum pooling is go like, suppose this is the current input, okay? And the pooling size 2 by 2 with a stripe by 2. So first, we just retain the maximum value, which will be 6. And then we move 2 pixels of the pooling window, okay? Then we just look for the maximum value for 2, 4, 7, 8. Then we retain 8. That's it, okay? Then next, we move 2 pixels downward and retain the maxima, which is 3, and then move it 2 pixels to the right and retain the maxima, local maxima value, which is 4. That's how we get it. And now, for this case here, we can change it to 4x4 into 2x2. Or you can select average pooling, which means what? For this case here, we 1 plus 1 plus 5 plus 6, that's 13. Then 13 divided by 4, we just put the average value. Okay. Well, actually, you can think of this if you can write your own code. You can replace this with morphology. The maximum pooling is nothing but dilation. And average pooling is smoothing. It's nothing but smoothing. So if you want to develop your own CL model, you can think of it with morphology. For example, you can go for top hat. Okay, based on your experience in assignment number 3, you can do a lot of things. But that's the typical idea. The only purpose is just to reduce the size. Okay. Let me say that one more time. You don't need to use pooling. If you go for convolution layer, okay, with the stride of 2, you will also reduce the size by a factor of 2. Okay. So let's skip some of the details. Okay, the pooling. Okay. And also, I just download some very important information or the terminology. Okay, you can go through all the details, but let me just highlight some of the important terminology for CNN. Okay, I will skip. Everybody know. Weight is the weight of the filter, okay, or the element of a filter, okay. The bias, you need to add a bias here, okay. Sometimes you can think of this bias as a threshold because the input and multiplied by the weight, then get some output value, and before you go for the activation function or anything else, you can compare with the bias. So somehow you can think of it as a threshold, okay? But anyway, that's the bias. A bias is also determined, okay, automatically based on your loss function, okay? So for this case, all the weight, okay, are the decision variable and also the bias here. Activation function, we already mentioned that. Activation, the purpose to obtain the nonlinear behavior, okay, of the output. The second one, we try to normalize the output value so that the range will be limited between 0 and 1 or -1 and 1. Okay, that's the most of the case. Okay, that's the activation function. Okay. So we do the multiplication or convolution of the input and the weight. Then we sum them up plus the bias, and then we input it to activation function, okay? And then the output, so that we can normalize the output value between 0 and 1 or -1 and 1. Okay, that's the purpose. And most of the time, this activation function is nonlinear. But let's take it one more time. The multiplication of the input and the weight is a linear combination, okay? Nothing but a linear. But when you go for a nonlinear activation function, the output becomes nonlinear, and the output value is bounded. It's bounded, okay? So here are some common use activation function. The most in the early day of the neural network, the most of the activation function is symbol. 在早期30几年前，那个 activate function 每个大家都用 symbol. Okay, here is the mathematical equation. X is the input value. Okay, here's the symbol. And then this is the sigmoid function. It means what? It will limit the value between 0 and 1. So if the input is 0, then the output will be 0.5. And no matter how large your input X is, it will bounded by 1. And no matter how negative the input value, it will bounded by 0. So for sigmoid, the output will be between 0 and 1. 0 and 1. Okay? This is the activation function by sigmoid. Okay? But nowadays, most of the CNN use red rule. Okay? Red rule means rectified linear unit. Okay? Rectified linear unit. It's so simple. Here. It means what? This is the activation function. It means what? If X is positive, then output is X. If X is negative, the output is 0. That's it. And it gives the breakthrough of neural network. Because in the early day, when your neural network goes stiff, you will get stuck. I'll explain that later on. Okay. I mean, the training will fail. When you use a sigmoid or any other very complicated, let me say that because the optimization is based on the gradient descent. 微分，还用梯度微分 is based on gradient. So when you go for the sigmoid, you take the gradient once, twice, third time, and eventually the gradient value will become 0. And then you will get stuck. You cannot improve anything. But if you go for the red rule, what is the derivative of X? What? X 的微分等于多少？好，好。For X, if you have a derivative of X, it will be 1. 1, nothing but 1. Everyone follow? 不是吗 ？X 的一次方嘛，微分不是1减1吗？不是0吗？就是 X 的零次方 ，X 的零次方就是1啊。Which means you take a constant. So simple, but it is a major breakthrough. So here's a decision function. Okay, if X is positive, then it just retain X. But if X is negative, everything becomes 0. You can think of this. So it is a constant. So when you take the gradient, it won't become 0. Okay? But it's so powerful. It solves a lot of problems, especially when your convolutional network it goes very deep. Okay? And you can think of this. When you stay at home, your mom or dad is nagging on you. You know what? 给你唠叨。You will bypass all the input, the noise. That's what exactly it's doing. Everything is negative, it's noise. You just bypass, okay? But it works, okay? It works, okay? So if you have no other choice, just go for red rule, okay? But for up-to-date model, they use a modified red rule. Okay, I will show you. Okay, the other very popular is called hypertension. Okay, it's very similar to sigmoid. However, the range is between -1 and 1 because for sigmoid the range is between 0 and 1. Okay, but for this one it's -1 and 1. If you go for the hypertension. Okay. The other very important one is the softmax, especially for classification. Usually softmax it will be used in the final output layer. 就是在最后的 output layer because what? Here's the equation. Okay, here's the equation. if you have a CNN, now we have, suppose we have a 3 output classes, okay? We have 3 classes. So this is A1. We have output A1, A2, and A3. Then we normalize A1, A2, A3 by this equation, by the explanation. So in this case, what? All the summation of x, will equal to 1. So, which means you can interpret, if we go for the softmax, now you can interpret this as the probability. It is the probability. Okay? So if this is 0.8, this is 0.1 and 0.1, then definitely this input x must belong to the class 1. That's it. Okay? And so for our case here, if for class 1, we have a 3 class, right? Class 1 and class 2. If we go for the supervised learning, the expected output should be 1, 0, 0. Okay? The expected output, okay, for class 2 should be 0, 1, 0. And for the third class should be 0, 0, 1. Okay? So that's it. So it's very important, especially when you use in the final output layer for classification. It's not even for segmentation. When I say segmentation, which means you can do the pixel-wise classification. But for this one, it's sample-wise classification. 做分割啦，影像分割，你就是 pixel， 每一个 pixel 你都要做分类。Okay, so you can go for the pixel-wise classification or sample-wise classification. But anyway, this is very important. Okay, usually we don't use in the intermediate layer. Okay, we just use red root most of the cases. But definitely we will use this one in the upper layer. Something I forgot to mention. I mean, red root is a breakthrough, but if you use this for regression, well, that would be one of the major topics for our data pattern, okay, course next semester. Anyway, if you apply the deep learning model for regression, don't use red root, especially the output could be negative. 回归啊，做回归啊，然后你回归的值有可能是负的话，千万不要这样用啊，以后你就完蛋，因为这样 ，you will never return negative regression value, right? Okay, don't use red root for regression in the last layer. Okay, it's okay. You can use in the intermediate layer. Okay, even for regression. Okay, so that's some of the. Here's a lot of red root. Okay, variant. Okay, let me say it quickly because the up-to-date model they use something like they modify. Here's what I'm saying. Okay, here's the red root. Okay, right? This is the red root. It's based on the maximum value. Okay, but some people find it will be too rigid Okay, just everything negative becomes 0 is not good enough. So some say, why not just retain a small value, a very small value, is so-called decade red rule. So it is a very small value. Alpha usually could be 0.01, for example, could be 0.01, but still linear, okay? Instead of set it to 0, okay? That's how the early days. But now some people say it's still linear, it's not good enough, or sometimes you will get stuck. So some people say, why not use, what could be the better way? We can go for nonlinear.
Use
Exponential. It is exponential. But when you use exponential, even sometimes you are getting larger, negative larger. So eventually, here comes the subtraction. So you will getting a large value, but later on, you will converge to 0 eventually. That's the activation function used in the up-to-date model. Okay, here's how it works. So decade red rule is just take a small value, okay? But it's linear. So if you are getting larger in the negative size, so some suggest why not use exponential linear unit, okay? So it's exponential, okay, like this exponential, but some further suggest is a scale exponential because if we are getting larger, right, in the negative side. So some suggest we put a scale, a very scale value. If you are interested, you can read the paper. It proves if you set x equal to this value, alpha equal to this value, you will get the best result. But I didn't put it myself, but it looks quite odd, right? With a lot of decimal point. But anyway, let's scale exponential. Anyway, you try to limit the value, okay, to be infinite large. Okay. And then someone suggests switch. It's getting closer to the activation function used nowadays. Okay, you will have a relative larger negative value, but not just close to 0. But eventually, you will converge to 0. Okay, that's the idea. Now, this is the one used nowadays. Okay, this is the one for most of the up-to-date model. It's based on Gaussian error, but still linear unit. Okay, the Gaussian error. A little bit complicated, but here's the equation for that. Okay, here's the equation for that. But anyway, take a look. This line is the Gaussian error. Okay, activation function here. Okay, this is an exponential. Okay, if you are getting larger, it's not good. Okay, don't use it. Okay, so you can use GE. Okay, so another one suggests mesh is used in YOLO form. Okay, again, but take a look. They all look similar. Okay, they all look similar. But apparently, Gaussian error dominated, okay, most of the up-to-date model, okay? So that's one of the activation function. I'm not quite sure Keras provide this function or not, okay? Otherwise, you have to write your own. But if you have no idea at all, just use the red rule. Just use the red rule, okay? That could be good enough in most of the case. Okay, so we already mentioned a lot of the cost function. Usually the cost function can be given by the mean square error, especially for regression, or for image reconstruction, for classification, what will be the loss function based on what you have learned so far?
Classification, softmax,
The major, it says softmax.
Yeah.
Now, softmax is just the activation function. But based on, right, that's good, but it's not, we are not finished yet. You will output the probability, then the probability must be compared to the ground truth. So the ground truth is either this cat, that's 1, or it's not cat, that will be probability of 0. So what will be the loss function? Entropy, got to be entropy. Got to be entropy, right? Right? Okay, so if this is a ground truth, and this is your estimate probability, right? This is the entropy. So if Fi, I should say, if the estimate probability equal to the ground truth, then it will be log 1, and log 1 is 0. Then you will minimize the loss function. So for classification, usually we will go for entropy, okay? So in classical, categorical, or binary, if it's just two classical, binary, categorical, cross entropy, or categorical entropy. But for regression or for image reconstruction, then we will go for the mean square error, okay? So again, A is the output, Y is the ground truth, okay? So that's it. So for the user, you need to determine what should be the objective function or loss function you're going to use. Most of the case, you select either mean square error or cross entropy, okay? Gradient descent, that's what I'm saying. Here's the equation of the L means your loss function. W will be the weight. Is the weight of your filter, okay? The weight of your filter, okay? And so on. So when we use the gradient descent, and eta here is now listen up, eta is very, very important. And for the user, you need to determine what should be the good learning rate. Okay, and it is an iteration. Now, T means the current, previous current iteration, then T plus 1 will be the next iteration. So we will update the weight based on what? Based on the gradient of the loss function with respect to the weight that you try to update. But eta is the learning rate, which is very important. Okay, it's very important. You can use the default provided by the programming code, but sometimes you need to make a change. This is just the example here. Okay, but you do it in a reverse way. You look for the maxima, but it doesn't matter. It doesn't matter. Okay. Oh, by the way, because in deep learning, you always look for the loss function, right? So in case you want to maximize something, if you want to max something, then you need to change it to, because loss function is try to minimize something, you need to change it to minimum, but just put minus sign here. That would be exactly the same, okay? Even you want to maximize something, you can change it, you put a minus sign here, then you can go for minimum. Okay, so we affect the requirement of, but anyway, let's go back. So first, for your application, first, you will look for the random starting point. So when you run your model and it fails, maybe you need to try some initial starting point again, okay? When you fail, it doesn't mean it won't work, but it didn't start with a good initial solution. Usually this initial solution is randomly given, but you need to start it from here. And then you will try to reach the top, okay, the optimal solution. So here, the gradient here tells you the direction, where to look for. Eta here will give you the step size, the distance to move, okay, the distance. So for this case here, we're starting from here, then based on the direction and the learning rate, that will be our next location. And from here, we take the gradient and then update, and then we look for which way to go and what will be the step size. Which means if the step size is too large, it might overshoot. For example, if we took a very large step, maybe it just hit this top here. But apparently, the top here is not the optimal solution. But if so, the better strategy, if you don't care about the computation time, always use a small learning rate. The price you need to pay is what? The computation time. You need a lot of computation time because each time you just move a very small step and look around and move, so it might take a lot of time, okay? So usually, we will do something like this. First, we use a large learning rate to move faster. And later on, we change the learning rate to a very small number so that we can look for the actual optimal solution. Okay? So you can keep the balance about the quality of the optimal solution and the computation time. Okay? So, but keep in mind, it's very important. And this is the reason why in the early days when people use simoid, okay, for the gradient, then you will get stuck here. Because when this value is getting smaller and smaller, then what? Then it will become zero. No matter what is your learning rate, then what? The weight at current time and the weight you are looking for the next time will be exactly the same. Then you get stuck. You won't converge. Okay, that's one of the reasons why you fail. Okay, but if you go for the red rule, I mean, it always won. It always won, and then everything just determined by the learning rate. Then each time you just move a very small step, and eventually you can find the optimal solution, right? To determine the weight or determine your filter. Okay. Okay, so that's it. Okay, so I just say the learning rate is very important. So it means if your learning rate is too large, so initially you will convert, you will improve the loss function very fast, but eventually you will lost. Okay, you will get lost. Okay. And if your learning rate is too small, then you will converge very slowly, okay? But if your learning rate is still high, then the loss will getting smaller very in the early stage, but eventually you won't improve anything here. So this is what we are looking for, a good learning rate, okay? Should be converged first, fast, but eventually it can go for the right, okay, solution. Okay, so actually is for the learning, we need to go. I will explain this. Okay. Let me show you some. Then I go back. So, okay, if you go to the page 39 something, Okay, you can take, I show you the example. We have an example like this, okay? It's MLP, but the operation is the same. The forward is first, you assign the initial value for W1, W2, okay? Then we calculate, based on the weight, we calculate the combination. And then finally, we output the value based on the current weight value you have. That's so-called the forward propagation. 第一个是 forward propagation。我们先假设我们已经有 W 的值，那我们就计算。Then backward is based on the output. We go backward, okay? We go backward based on the current decision value. Then we go backward, and here's how we do the backward. Okay, when we do the backward, we need to take the gradient. Okay, E total is the output. Okay, we take the gradient with respect. For example, you want to know what should be the best value for the fifth weight. Then we can go for the chain rule. Okay, because then we can take the output. Okay, you can cancel out. See that the output can cancel out. The derivative of net can be cancelled out. So it will be the same. So next, we just calculate the value for this one, and this one. That's the backward propagation, just like this. Okay, once you have the output value, then we go the backward. Okay, go the backward. Based on the activation function, based on what is the output of the hidden layer 1, and then we can go back to the initial value. That's called backward propagation. Okay, so if you want, you can just check for this example to understand what do I mean by forward propagation and backward propagation. Okay, everything will based on the gradient. Okay, now we can go back. Okay, let me go back. Where's the pages? Should be. Okay, I have explained what do I mean by forward propagation, backward propagation, and then here's a page. Okay, usually when we solve for the ultimate solution, we don't input the whole data set. Instead of we divide it into small batches. So the minimum batch size will be just one sample. Okay, the maximum batch size will be the whole training data. But usually, now it depends on your application and the hardware, software you can have. Usually you can go for a batch size of 10 or 20, okay, and then so on. So, and then we solve for the ultimate solution based on this batch. And then, now listen up, the batch, when you do for the, carry out the batch, you need to use shuffling first. Especially when you collect the data. For example, you want to identify male, female, or cat, and dog samples. You might have something like this cat, and then the next half of the data set will be dog. Then in this case, if we go for the batch, all the sample will be cat, and there's no dog. Then you will get into trouble because what it can learn is just cat. So you need to do this random shuffle. 就是像那个打桥牌要洗牌，先洗牌。Okay, do the random shuffle. Okay, random shuffling, so that when you do the batch, it will contain the cat and dog and all other classes. Okay, you need to do that. Don't just go for from the data you collect. Okay, so that's the. Now, let me finish this, and then we can take a break, okay? Apex. Apex is nothing but a single iteration of all batches in both forward and backward. It means what? One apex is a single forward and backward for all or for the entire input data that called epoch. Now, if you are you don't like this terminology, you can think of it as iterations. Iteration 就几个递回运算，可是它的一个递回运算呢，就含一个 forward 跟一个 backward， 可是要对所有的 for all training sample, even if divided into batches, okay, you need to carry out this for all batches. So if don't care about the training time, use a large, right? Okay, apex, that would be better. Okay, but usually we just start a small value and take a look about. Always print out the loss function value. Okay, as a function of apex. And see if you see something like this, then you know something wrong, or you might have to change the learning rate. Okay, to make sure eventually it will converge. Okay, always print out something like this. So don't set up the epoch, for example, 1 million and run it for 1 or 2 days and come back to take a look. Then you will waste a lot of time. Okay, just try to run a small epoch and see what will be the loss function look like. Okay, if you have something like this, then you have a good confidence about the learning rate. Okay, so anyway, and then you can increase the number of iterations and then to see if it converge or not. Okay, so always print out this loss function. Okay, this loss value as a function of iterations. Okay, let's take a break.